Hello everyone, I'm Hao Guo from Tsinghua University. Today I'll present our work, OdinANN, direct insert for consistently stable performance in billion-scale graph-based vector search. This is a joint work with my advisor, Professor Youyou. Vectors are powerful data representations. Raw data, such as text and image, can be encoded to high-dimensional vectors using embedding models. These vectors have desirable features. For similar data, for example, cat and cat face, vectors are near in distance. For different data, for example, cat face and glasses, vectors are far in distance. Therefore, vector distance reflects data similarity. Leveraging this, we could conduct similarity-based data retrieval using vector search. Vector search requires a vector index, and we focus on graph-based indexes due to their search efficiency. In the graph-based index, each vector represents a node. Similar vectors are connected using edges. We denote the query or target vector using a star. Vector search starts from an entry node and finds the top k nearest vectors to the target vector in a best first manner, like this. Sometimes, new data needs to be ingested into the vector index. At this time, a new vector needs to be inserted into the index. To do this, first, find the candidate neighbors of the target vector using a vector search. All the visited vectors could be the new vector's neighbors. Second, add bidirectional edges to the new vector and part of the candidate neighbors. Some real-world workloads need to support vector inserts in large-scale vector indexes. They typically contain billions of vectors and need to insert 100 million vectors per day. To meet this demand, a cost-effective solution is to store the vector index on SSD and make it support vector inserts. Existing solutions to support vector inserts can be divided into two types. The first one is to periodically rebuild the index. However, this process requires several days for the large-scale scenario. For example, a dataset with billions of vectors. In this case, building an index requires several days, which is unacceptable. The second one is buffered insert. Inserts are first conducted in an in-memory delta index. Then, the in-memory delta index is periodically merged to the on-disk full index. Intuitively, this process can reduce SSD writes by merging the updates to the same graph node. However, we find this process has trade-offs. First, the in-memory delta index consumes a significant amount of memory. For a billion-scale dataset, inserting only 3% of vectors requires 100 gigabytes of memory. Second, buffered insert interferes with front-end search tasks when merging the inserts to SSD. The search latency increases to 2 times compared to that without merging. Third, the merge algorithm itself only merges updates to the same node, but inserting memory, which mainly includes finding candidate neighbors using SSD reads, is still executed one by one. We find that the merge throughput is bottlenecked by this process due to read bandwidth contention, regardless of the merge batch size. In this work, we explore another trade-off, namely directly insert vectors to the on-SD index without merging. We call this process direct insert. By doing so, the memory overhead of in-memory delta index is eliminated, and the merged overhead is amortized across the timeline. However, challenges occur for efficient direct inserts. The first challenge is SSD write overheads. Inserting a vector updates its hundreds of neighbor records to add bidirectional edges across them. Unfortunately, neighbor records are scattered in different pages. Updating them introduces hundreds of SSD writes for each insert. To tackle this challenge, we seek to merge multiple neighbor record updates into a single page. Our key observation is that records in the graph index are of fixed size. The graph index is organized as adjacency lists on SSD. For example, the adjacency list for vector 1 contains the vector itself and its out neighbors. The vector is of fixed dimension in a dataset, so it is of fixed size. The neighbors have a maximum count of r, so it is also of fixed size. In total, the record is of fixed size. Leveraging this, we could do auto-place updates for records. If we update records 2, 5, and 7 in page 3 with a single SSD write, then the old records, namely 2 in page 0, 5 in page 1, and 7 in page 2, can be directly reused as empty slots without explicit garbage collection, like merging them into a continuous range. Based on this idea, we do over-provision in the SSD layout. By default, we preserve 2 times of the space, then each page, on average, contains a half of empty slots. Then, we could merge updates in the multiple free slots of a page. For example, if we want to update 4 records, 2, 5, 7, and 9, then we could merge the updates of 2 and 5 in page 1 and 7 and 9 in page 2. Then, the original records 2 and 5 can be marked as empty slots without extra overheads. This reduces SSD writes from the original, like 4 or 3, to the new writes to 2-page writes. The second challenge is concurrency control. Insert and search may access the same records. For example, insert C needs to update 2, 5, 7, and 9, and search 3 needs to traverse 2, 4, 5, and 6. These 2 processes both access records 2 and 5. They need concurrency control to ensure the consistency The trivial idea is to lock the involved records in the whole process. For example, lock 2, 5, 7, and 9 for this insert. However, each insert takes tens of milliseconds, so the critical section is long, which harms the performance. To tackle this challenge, we propose approximate concurrency control. The key idea is that search and insert are both approximate processes. Search returns an approximate set of top k neighbors of the target vector, and insert finds an approximate set of top k neighbors as the candidate neighbors of the new vector. Therefore, operation-level locks can be relaxed to record-level locks. Specifically, based on this idea, we relax the concurrency control mechanism to record level, namely, only ensure that each record read and updated is correct, but not necessarily the same version. The search process only acquires the lock when accessing a record. For example, this process sequentially accesses 2, 4, 5, and 6. It only locks and reads 2 during when it accesses the 2, and unlocks 2 immediately after the access finishes. There is no need for the search process to wait for the whole operation to finish when unlocking the records. The insert process first finds neighbors like the search process. It only acquires locks when accessing a record. Second, to avoid update losses caused by concurrent inserts, we grab locks to all the records to be updated and reread their newest version. This is the validate process. Finally, update and unlock them. By doing so, the critical section of update is reduced to a single parallel SSD read after write. Write after read. Put them all together, we propose OdinANN. It uses direct insert to reduce interference with front-end search, and uses 2 techniques for efficiency: update combining for reduced write amplification, and approximate concurrency control to shorten the critical section. If you are interested, check our paper for more details. Next is our evaluation. We compare OdinANN with on-SSD updatable vector search systems, including graph-based FreshDiskANN and cluster-based SPFresh. We use both 100 million scale datasets and billion scale datasets for evaluation. Here, we show the overall performance of billion scale vector search and insert. The setup is that we achieve insert queries per second is 1,000 and search query per second larger than 5,000. At these settings, OdinANN has a stable performance as shown in the red lines of the three figures A, B, and C. It achieves low and stable search latency, both for median latency, 90% latency, and 99% latency, compared to all the other systems. Meanwhile, it achieves a stable throughput and unsacrificed search accuracy compared to graph-based DiskANN, and it has less memory usage compared to graph-based DiskANN. Compared to class-based SP-Fresh, it achieves higher search accuracy and higher search throughput. Thank you for your attention. OdinANN is integrated into our PipeANN system, which is a vector store achieving low latency, large scale, and updatable simultaneously. We welcome conducting research based on PipeANN, and we welcome any contributions. Thank you.